So a lot of people are confused on how to actually start with a control unit. We spent a lab just messing around manually with the control lines, so at least now we have sort of like an understanding of what each control line does. And how do we build a circuit that takes an instruction and then interprets which control lines to use? So that's the goal in the control unit. And how we do that, the best way to do that, is to basically write out all the possible instructions that the computer can perform, the encodings of each of those instructions, and then we're going to draw out this great big table writing what the state of each of those control lines should be for those instructions. So I'll spoil a couple of them, but leave the rest for you to do. So you'll also notice that I've sort of combined all the ALU operations and or add, subtract, and an or into the one instruction, because they're all kind of sort of the same thing. They all kind of act in the same way, in that you read two registers, you add, subtract, you do whatever operation needs to be done, and you write it back to a third register. So all the control lines are going to be more or less the same, with the exception of the operation we tell the ALU to perform. So let's have a look at WS, write select. This dictates which register is getting written back to. So when we perform any ALU operation, the destination register, that 3 bits in the instruction, is going to tell us where to write back to. And in fact, this is going to be the case for every instruction, because every instruction writes back to the destination register, with the exception of store, because store writes something to memory. So when I do a store, I don't actually really care what the destination register is, so I don't really care what write select is set to. And then for load, it's also the destination register is RD. And this means that the write select control signal is actually pretty easy. It's just the 3 bits of the destination register. So in digital, we can just hook these 3 bits straight to write select. Notice for the moment I'm totally ignoring conditional execution on the Z bit. You'll have to work that one out yourself. I'm just assuming the machine that we covered back in Lab 5. So let's have a look at another one of the control signals, the DMUX. The DMUX is a bit of a tricky one. So recall from Lab 5 that the DMUX had a 2-bit input, and this was how it was configured. So 0, 0s read from ALU, 0, 1s read from memory, 1, 0 was read an immediate from the instruction itself, and 1, 1's reserved for future use. We'll ignore the SETH instruction for the moment because that was in Lab 6. We'll focus just on the core instructions. How do we write out the table for DMUX? Well, if it's an ALU instruction, the DMUX code is going to have to be 00 because I'm reading from the ALU. If it's a MOVL instruction, I want to read from the immediate encoded in the instruction itself, so that would be 10. A store is writing something to memory, so I guess it doesn't really matter what the DMUX is because we're not storing to a register. And to load something from memory, we're going to be obviously reading from memory into the register file, so we set the DMUX signal to 0, 1. Now, how does that help me build a truth table for it? Well, we can consider DMUX to actually be 2 outputs. We have the first bit of the DMUX, and we have the 0th bit of the DMUX. So we can sort of split this signal, and we just get rid of the other control signals for the moment, into 2 parts, as follows. So it doesn't really matter what the signals are when there's an X, so we can pick whatever makes it easier for us. So in my case, I'm going to put a 0 for both of them, because now it means that these bits are only true for one particular option. So in this case here, I can read off from my table that the first bit of the DMUX is given when we are performing a MOVL. And then when am I performing a MOVL? Well, that would be when the opcode is all 0. So we need some way to check that the opcode is all zeros. So opcode equals quadruple 0. And then the 0th bit of the DMUX is when we're performing a load. So in this case, when the opcode is 0, 1, 0, 1. So I guess what we have to do is in digital, we're going to split up the DMUX signal. So we take 2 1-bit inputs and we return 1 2-bit output. And now I need to build a circuit that's true when the opcode is all zeros. So if you can imagine, I could write out a truth table considering the opcode to be 4 bits. Truth table will look a little bit something like this. When all the opcode bits are 0, then the first bit of the DMUX is 1, and for any other case it's 0. Well, we can just AND the negation of all the opcode bits. So that is negation opcode bit 4 and negation opcode bit 3 and so on and so forth. AND them all together, and that will tell me when to assign 1 to D1. So I should get an AND gate. Number of inputs is 4, and then all the inputs is inverted because I only want this to be true when all the opcode bits are 0. And so then we can just route the opcode bits down. So I like to draw straight lines like this because it means I can easily add more gates afterwards. And then we just tap in the connections for the AND gate. So that tells us the first bit of the DMUX. I've got to be careful here. This is the 0th bit at the top. This is the first bit. So I'll route this cable down like that. In fact, maybe we'll bump this whole thing down a bit to make it look a little bit cleaner. There we go. And then it would also be a good idea to add a label for what exactly this AND gate is doing. So under, where are we? Components, miscellaneous, decoration, text. I put some text. So now I know the output of this represents whether or not I'm doing a Movell instruction. So what else do I need to do? So I want D0 to be high if the opcode is 0, 1, 0, 1. So I can use another 4-input AND gate. I want it to be 0, 1, 0, 1. So I want the first input to be negated, the second one not, third input negated, fourth one not. And then this represents the highest bit in the opcode. So that's opcode bit 3, opcode bit 2, opcode bit 1, opcode bit 0. I'll put a label on it. What does this represent? It represents if we're doing a load instruction or not. And then I can plug that into the 0th bit of the DMUX. Assuming all the other outputs are disconnected, if we run the test for this, we'll find that the test will pass, or at least all the times that we're not executing a SETH instruction, because at the moment I'm not testing for that because I haven't implemented it. So that's a couple of the control lines. Your job is to work out if you added the SETH operation to this, how would that change what the outputs have to be set to, and how would that change your tables? And also you have to work out all the rest of the control lines. So the control lines for the register file, whether to store and load, whether to write to a register using the write enable, and of course the ALU operation itself.